As we march toward a method for finding the exact area under a curve, we're going to take what we know about estimating the area under a curve and add one more step, which will take us to the exact area. Before I do, I think we should have a little discussion about partitioning. There are multiple methods for partitioning an area under a curve or partitioning a curve to estimate the area. We spoke about yesterday, suppose this was a first partition, we would have a lower partition, or I could go all the way up to an upper partition, and I might choose all lower partitions to underestimate the curve, or all upper partitions to overestimate a curve, or the method I'm going to use today, once we've decided on our partitions, then I'm going to use something called the right-hand partition. That means that the upper right-hand corner of my rectangle has to be on the actual curve. So in this first partition, it looks like a lower partition. But if I come to, well, this next partition also looks like a lower partition. But let's see the third partition. If I go up and hold the upper right-hand corner on the curve, it actually looks like a higher sum. And then once I get to this last one, what is that? Oh, that also looks like a higher sum. So I have what looks to be two lower sums and two higher sums. It's just another partitioning technique. It's an estimation to get you somewhere close to the curve. The algebra is the same, or the formula for the sum is the same. You have however many partitions, and you're going to count from the first to the nth one. And the area of each partition is determined by the height, which is the f of xi, and the length of the base, which is just delta x. Another commentary is right now, and I will continue to do evenly spaced partitions so that delta x will be divided into even bases, even intervals. So if I've divided this interval from A to B into 4 partitions, each partition is 1/4 of the total. It's not required. The partitions can be randomly sized or differently sized. Those are Riemann sums. I'm not going to do that because sometimes I think too much is too much when you're learning something new. You can save that explanation for your college professors. And they're nothing to be worried about. The calculations are very simple. They're just more. And sometimes more is just more. So let's get back to evaluating the exact area under the curve. Notice on this second partition, if I were to divide it into 2 more, or divide it in half, right? So originally my underestimation was this giant-sized rectangle, but now if I were to divide it in half and make a right-hand partition, or 2 right-hand partitions out of it, notice that now I'm closer to the actual value on that interval because this part is no longer part of the included in the error portion. So I've only divided one of the partitions in half, and I've already gotten closer to the actual area. So if I were to divide or partition all of them in half, thus doubling the number of partitions, then I would have, I can do this and talk at the same time, there we go, then I would have an even closer estimation. So only doubling the number of partitions, or my n value, gets me closer to the actual area. So if I were to split them and double again, I would get closer and closer until, if I took the limit, as my partition sizes approached infinity, or the number of partitions approached infinity, meaning they get thinner and thinner and thinner, then I would arrive at the actual area of the curve. So let's do that with an example. So we want to find the area under the curve, f of x equals 2x, and bounded on the x-axis by x equals 0, x equals 1, and we want to keep it above the x-axis, so y equals 0. That means we're looking for the area that's bounded by the y-axis at x equals 0, and the x-axis on the interval from 0 to 1 and everything below the curve. So first I need to partition this. I need to divide it into partitions. And we remember how to do that. That's the change from one x to the next x to the next x value is the entire region, whatever that length is, so b minus a, over n. In this case, I've sketched in n is equal to 5, 1, 2, 3, 4, 5 partitions, but we're not actually going to restrict ourselves to an actual number. So b minus a is 1 minus 0 over n, which means 1 over n. That means each partition is 1/n of the distance from the start to the end. In this case, it would be 1/5 and then 2/5 and then 3/5 and then 4/5 because n would be 5 partitions. All right, so now we need a value for my x ordinate. We know in the example of 1/5 that this is 1/5, 2/5, 3/5, 4/5, so we have something to plug into our function to get the height at that point. But we're not trying to use fifths, we're just trying to find a way to describe my x value at each iteration. So from a to the first one, so x sub I, my random x value, is whatever a is plus however many times I've incremented forward on the x-axis, I times delta x. So my change in x is 1/5, and if I go to the third one, then it's 3/5 would be my x ordinate. All right, so in this specific case, we're looking at a equals 0 plus I times, well, delta x is 1 over n, or simplified, I over n. And that fits in our 1/5 example. The first iteration, I is 1, so 1/5. The second iteration, I is 2, so 2/5. The third iteration, I is 3, so 3/5. All right, that's enough on that. All right, so let's go ahead and put together our formula. We're not going to take the limit yet. We're just going to take the sum. So the sum for partitions starting with the first and ending with the nth of f of xi times delta x. And lucky for me, I actually have all these values. I have xi is I over n, I have delta x is 1 over n, and I have a function value which is 2x. So I can just rewrite this using all those values. For the function is 2 times xi, I over n, times delta x, 1 over n. And now I can clean this up even more. 2i over n squared. All right, so a little side note. I'm going to rewrite this formula. I want it to say the sum as I equals 1 to n of 2 over n squared times I. I want to pull that I out. If I can do it algebraically, it's smart to do it now. I'm going to show you why that's a good idea, and then it'll just save you steps later. If you have to take the steps while you're learning, no big deal, but this is why. Suppose I didn't and I started here. The sum I equals 1 to n of 2i over n squared. So if I operate this sum, I'm going to start with I equals 1, so I have 2 times 1 over n squared, plus I equals 2, 2 times 2 over n squared, plus I equals 3, I equals 4, right? I'm going to just keep adding it in until I finally get to 2 times n over n squared. Now look what I have. I have 2 over n squared in every term in my sum. So if I factor that out, I have 2 over n squared times 1 plus 2 plus 3 plus 4 plus 5, on and on until I get to plus n. And this is useful because I actually have a formula for this. Remember, this is Gauss's formula for my I, that the sum of I equals 1 to n is just the formula sum consecutive integers. n times n plus 1 over 2. And so now I can clean everything up, just put it all in my formula. I have the sum I equals 1 to n of 2 over n squared. And since I have a formula, I don't have to carry out my iterations to infinity to figure this out. I have a formula. So I'm going to put in n times n plus 1 over 2. But that's the sum, starting with the first partition, ending at the second, of, if I distribute, I get n squared plus n, and then multiply each by 2. I get 2n squared plus 2n over 2 times n squared. Okay, well, this reduces, right? 2 over 2n squared equals 1 plus 2n divided by 2n squared. The 2's cancels, one of the n's cancel, and so I get 1 over n. And now I have a sum that's super easy to work with. Let's bring it over here. I'm just going to rewrite it. And I'm going to take the limit now. Okay, so I can break this up. Remember, when I'm dealing with limits and with sums, if I have two terms, I can make them two separate entities. So I'm going to take the limit as n approaches infinity, that means the partition size, a number approaches infinity, of I equals 1 of n 1 plus the limit as n approaches infinity of the sum of I equals 1 to n of 1 over n. Well, this is just a constant using constant multiple rules. That equals 1. And in the second case, if I plug infinity in for the n value, meaning if my n values, if my denominators get bigger and bigger and bigger toward infinity, then the whole value of the number gets closer and closer to 0. So that 0 plus, or 1 plus 0. So that says that the area under my curve equals the limit as n values approach infinity of this sum, which equals 1. I'm saying that the area under the curve equals 1. Now, we have a way to check this, lucky us, because this is a very simple shape, and so we can calculate the area using older math. F of x equals 2x is just a line with a slope of 2. And we want it on the interval ending at 1, between 0 and 1. So we know that the area of a triangle is 1/2 base times height. That means we're looking at 1/2, well, the base is just 1 times the height, but the height of the triangle is whatever the function value, the f of 1 value is, right? Times the f of 1. But that's 1/2 times 1. Well, the f of 1 is 1 times 2, which equals 2. 1/2 times 2 equals 1. So the area of this triangle equals 1. We can find it using simple geometry, but as soon as we get even slightly more elaborate in a function, and even the next step up, which would just be f of x equals x squared, we have no geometry to calculate. All we can do is estimate by partitions. But if I use the sum of partitions and take the limit as there are infinitely many partitions, even under f of x equals x squared, I'm going to end up with an area that I can use. And by area I can use, what I mean is the exact area under the curve. So I've now calculated the exact area. And that's pretty cool if you ask me.